that my little video capture won't do more than an hour at a time. Okay, first thing, draw a picture of the moment in time, right? Draw a picture of the moment in time. Now, here's the thing, I'm curious to see how this is going to work out. The whole purpose of today's lecture is for me to show you these problems for the first time so that you kind of see how they work. Your challenge is going to be you're not going to have a drawing, you're not going to have a picture, you're not going to have all this stuff. You're going to have to read it and then from that extrapolate the picture. That's going to be the hard part for you. I mean, one of the hard parts, right? So here's my picture of the moment in time. I have the ground, I have the radar station here, I have the plane. So here's where if you're an artist like me, you can really start to show off some of your skills. Okay. Oh, you want a radar? I'll take care of that. There's your radar. Okay. So there's your radar station. Look at that. Beautiful. And what can I say? At this moment in time, it's what? 6, right? And what can you say about the distance from the plane to the ground? It's 2. But is that 2 changing? No, there's a difference now. This is the first time we've seen a problem where there's something in the problem that's constant all the time. Even when it's changing, it's still the same, right? We haven't had that yet. With the spheres and the circles, if the radius changed, the volume changed. If the area changed, the radius changed. Everything was connected. Here, that 2 is always the same in the entire problem. Very important that you understand that. Okay, that's the specific instant in time. Now a general picture. A general picture, this airplane is moving, right? So now, when it's moving, can I say that this is 2? Yes. Can I say that this is 6? No. So let's call it something. It's the thing I want to measure, right? It's the thing I want to measure? But it's changing, so I have to assign it some variable. Go ahead, give me a variable. D. That's the most common one that we'd want to use, right? D for distance, maybe? I would avoid D, and here's why. You'll have DDDT, which is just a little weird to write. DDDT. It's just a little strange. You can do it. I always avoid D, little d. In any problem I ever do, I don't ever use little d. You can if you want. I won't. So I'm going to call it something else. I'm going to call it H for the hypotenuse. It's the hypotenuse of a triangle, isn't it? It's a hypotenuse of a right triangle. So I may as well call it H. So H is changing, isn't it? Is there anything else changing in this problem? Yeah. On that triangle that I've kind of forced you to draw here? What's changing? The bottom? This right here, right? This right here, the distance from the radar station to straight down from the airplane, that distance is changing also. Now that's not what I'm interested in though, right? H is what I'm interested in, how much that's changing. But this is changing also. So, okay, let's label it. It's kind of like the x-axis, isn't it? So why don't we call it X? Now, when you're drawing your picture, sometimes you might want to actually sit here and be doing these at the same time. Your general picture and your given and your want at the same time so that you start to kind of like fill in the pieces. What am I given in the problem? Altitude. Altitude is 2 miles. I've covered that in my pictures, haven't I? Okay. What else? How fast the plane is going. How fast? That's a speed. It's a rate of change. Of what? D what? DXDT. The speed of the plane is how fast it's going straight across, isn't it? Isn't it? But that's also the speed at which this side is shrinking. See, as the plane moves, this point right here moves also. So this length is shrinking by the same amount that that plane is traveling. Now, it's shrinking, right? X is getting smaller, not bigger. This is where the sign comes into play. I'm going to look at this. We are given that DXDT is negative 600 miles per hour. Why negative? It's getting smaller. Do you see that if we drew our triangle the other way, then this would be x, and the plane would be going away from us, and then dx dt would be positive, because the x would be growing. See the difference between those two? Now, that's the other way if we did it the other way. That's not the way we've chosen to do it. But you got to pick up on that negative 600, though, because it's a shrinking variable. All right. That's what I'm given. What is it that I want? How fast the distance between them is changing, dh dt. That's what I want. When do I want it? At exactly the moment what? What's 6? At exactly the moment what? That what is 6? The distance between them. What in your picture is the distance between them? H. You've got to have everything assigned to something. All right? Everything, every number you have, every number, every rate must be assigned to some variable, and that variable has to somehow appear in your picture. Any questions? All right. That's pretty much it. I don't think we've left anything out, right? As far as what's given? Yeah. So, connect them. Connect your variables. What variables are we trying to connect? X and H, right? X and H. X and H. How can you connect X and H? Someone give me an equation that connects X and H together. That's true, you could. That's probably more than you need at this point, though.
H equals to H. What? H equals to X. Wait.
I'm waiting. You know, everyone's making this harder than it has to be. Okay. Yeah. What?
Perimeter. A plus B plus C.
That's what kind of triangle? A right triangle? That's a right triangle? Pythagorean identity? A squared plus B squared equals C squared. Right? A squared plus B squared equals C squared. For any right triangle, right? Any right triangle, I have to erase something here. If you watch my video, I said in the beginning, be prepared, because now these formulas that just exist out there, they may come into play at any point in time. If you have a right triangle, if this side's A, this side's B, and this side's C, the relationship between the sides is that A squared plus B squared equals C squared, right? That's Pythagorean identity. In fact, that's the identity where we get the trig identity, sine squared x plus cosine squared x equals 1 from. But that's the even more fundamental identity we need. So can I, from this equation, from that identity, create an equation connecting those together? Absolutely, right? What is the relationship between this? X squared. So this is step 4. X squared plus 2 squared, which is 4, must equal 8 squared. You now have an equation connecting X and H together. Once you have the equation, you differentiate it implicitly with respect to time. All right. What is the derivative of that with respect to time? 2x. Oh, careful. Yeah, dx dt, right? I used x kind of on purpose here because I was curious to see if we would just say 2x and say, oh, it's 2x because it's always been 2x, or if we're actually going to remember we have to put the dx dt on that because we're differentiating with respect to time, not x. So the derivative of x squared is 2x dx dt, not just 2x. Plus 0 equals 2h DHDT. Now I'm going to inspect my equation to see if I have everything I need. Do I know x at the moment in time? Well, in my general picture, no, right? But in the specific picture that I had, when this was 6 and this was 2, couldn't you find out what that is? How? Pythagorean identity, right? A squared plus b squared equals c squared. You could figure out what that is. So I'm going to be able to get x, right? I'm going to have to do a little work, but I'm going to get x. DXDT, that's the speed of the plane. I have that. H, that's the distance between the plane and the radar station at the moment in time. 6, I have that. DHDT, that's what I want. So I'm in business. Let's find x though. So I'll come back to this picture. I'm just going to replace this with x right here. And so I have x squared plus 4 equals 36. So that means x squared equals 32. And that means x is equal to root 32. A squared plus b squared is c squared. So my equation should be 2 root 32. dx dt was what? Negative 600 equals 2 times h was 6, dh dt. So let's see, this side becomes negative 1200 times root 32. And then what's this side over here, 12? And then divide through by 12. Somebody on their calculator give me this as a decimal. It's the 1200 divided by 12 just becomes 100. So it's a negative 100 times root 32.
Negative 565.
Yeah, negative 565. Yep. 0.7, let's say. Negative 565.7. Approximately dH dt. What do you got? What do you think?
Miles per hour?
Yeah, miles, that's what I was going to ask you next. Units. H is the distance between the two. Distance has been measured in miles in this problem. And then time, everything has been measured in hours, not seconds. So this should be mph, miles per hour. That means that the distance between them is actually closing, right? Negative means that it's coming together at a speed that is slightly slower than the speed of the plane itself. Could it be possible that the distance between the two is ever faster? The distance between them is closing any faster than the plane is going? Could you actually have that happen? Think about it. But even, let me think about it. If the plane was aiming towards the radar station and going towards it at 600 miles per hour, then the fastest it would ever be going towards it is 600 miles per hour, right? So we should never be able to exceed 600 miles per hour, ever. Ever, ever. Yeah, okay. Y'all hanging in there? We still have 35 minutes. Y'all all right? Next problem. The street light problem. I like the street light problem.
It's fine.
So this guy is just mugged someone, right? down in a parking lot in Walmart or something, and he knocked over the person and took their stuff, and then now is running away, trying to get away. And there's a street pole with a light on top of it. And so as he's running away, right, the calculus person that's observing doesn't call 911. They ask themselves, they say, I wonder how fast the tip of the shadow of the person is moving away from the base of the pole of the, how fast is that shadow moving away? That's what we want to ask. So does it make sense though? I mean, like if I had a light shining behind me, then I have my shadow on the ground. As I run, right, then my shadow starts to move out in front of me, doesn't it? The further I get, the longer my shadow is. And so I would like to know at a certain instant in time how fast the tip of my shadow is moving away from the pole. Now there can be a little confusion in this question, because if I'm running, then the shadow's moving away from me, right? But I'm moving too. So the rate at which it's moving away from me is different than the rate at which it's moving away from a pole that's not moving. Does that make sense? It's moving away from the pole faster than it's moving away from me, because I'm moving in the same direction as the shadow too. Does that kind of make sense? So in these word problems, every problem I've given to you right now is these are all classic Calculus 1 problems. And sometimes they vary them a little bit. And one of the problems that they'll ask is, how fast is the shadow moving away from the person as opposed to away from the pole? So there's a slightly different attack you have to have for the problem. Okay, so I can actually pause this, snap to the instant in question. So I'm going to read the problem here. A street light is mounted on a 20-foot pole. 6-foot man walks away from the pole at a speed, at a speed of 7 feet per second. How fast is his shadow moving along the ground relative to the pole when he is 12 feet from the pole? So at exactly this instant, when he's 12 feet away from the pole, how fast is the tip of his shadow moving away from the pole? He's walking. He's got huge strides. He's walking fast. Trying not to be, trying not to make a scene, trying to be inconspicuous. Doesn't want to be running. Okay, now the big thing is, could you have drawn this picture without me drawing it for you, right? Like, could you have come up with this? So let's see. I'm going to draw my picture, time in question. Okay, at the instant in question, I would have, what, a 20-foot pole here, right? Here's my light source up there. I've got my person who's running away or walking fast, like that. Again, don't let my artistic skills intimidate you here, okay? Don't let that. If you can't draw as good as I can, please, it's okay. Just use a basic stick man. Don't go with the advanced one. Okay. What should I put here next at the instant in question? How far is he from the pole? 12 feet from the pole, right? So this is fixed, right? For the instant in question, that's fixed. And he's 6 feet tall. And I don't think that's going to change, because he should stay 6 feet tall the whole time. Okay, got it? All right, that's the specific moment in time. Now the general, I don't have his shadow, right? But his shadow would be on the ground here somewhere. And it should be directly from here. Should be down here somewhere like that. And again, don't let my artistic abilities, look at that, that's his knee right there on the ground, and his leg. Look at that. I even elongated it. It's proportional. I know. Are you thinking that I should be an artist instead of a mathematician? Okay. I'm just trying to find some humor in this, all right? Because it's so much fun. Let's draw the general picture. If I draw a general picture, then the only things that should stay the same are the 20-foot pole, right? The 6-foot man. And other than that, everything else changes, doesn't it? That means the distance from the person to the pole changes. And I'm going to call that the same thing I call it in here, which was, well, actually, I didn't call it X. Hold on. My drawing goes like this. You could do it either way, but I'm going to do it the way I did it on that picture in there. I did the distance from the tip of the shadow to the pole. I called that X. And I called the distance from here to here the shadow. I believe that's what I did. Yes. That's S for shadow. Do y'all agree with that? What I don't have represented here is part of what I've been given and part of what I want. So now is a good time to probably put down what I'm given and what I want. What am I given?
The height of the pole.
The height of the pole, got that. It's in my picture. It's not changing. 6-foot man, that's not changing. Somewhere I need a D something, right? Somewhere? 7 feet per second. That's the rate at which the man is what? Running, moving, right? So where is that in my picture? What variable is that in my picture?
That would be the H. Right?
Where's H? I don't have an H yet.
That would be the X.
That would be from the pole to the guy, which I don't have represented in my picture, do I? I need that in my picture. Because I need to call it something, right? Now be careful. It's not how fast this is changing, right? That's how fast that S stands for shadow, by the way. That's the 7 feet per second isn't how fast the shadow's changing. It's not how fast the distance from the pole to the tip of the shadow is changing. It's the rate at which the distance from the pole to the man is changing, and I'm going to call that R. So I'm given d r dt to be what? 7 feet per second. What is it that I would like to find? How fast is his shadow moving along the ground relative to the pole? DXDT. See, because if you look at just the shadow, how fast S is changing, that would be the rate at which it's changing relative to him. But you want it relative to the pole. So that would be X. So you want DXDT. When do you want DXDT? At what's 12 feet? At the moment, what? When he is 12 feet from the pole. So when R is 12. Does everyone see where all those things given and wants come from? Anybody have a question? Anyone have a question as to where I got any of that?
So R is the speed he's running, right?
R is the speed he's running, yes.
So we want to when his speed is 12.
No, that's because it says, how fast is his shadow moving along the ground? That's DXDT. When he is 12 feet from the pole, not running 12 feet per second from the pole. When he is exactly 12 feet from the pole. So what variable did I put in here that I actually haven't even used in here? S, right? There's no S, but I'm going to leave it there for now. Okay, here we go. I need to find a way now to connect R and X together. And maybe I'll just take the S out of here just for now, just so you can focus on just the two things I'm trying to connect together. erase this.
R is some portion of that.
R is what?
Some portion of that.
Some portion of x. So yes, I agree with that. Yes, they're
Divided by
R divide. Are you just
Just throwing it.
are you throwing that out there, or you have?
X.
So watch this. Right, here's our light that's coming and hitting his head, right? Do you see two triangles? You should see a large triangle. That's this one, x and 20. Right? You see that one? That's this big one. That's one triangle. And do you see the smaller triangle here? See that one? Right there? So that one looks like this. This side is what? 6. What is this side? Be careful. What is this side?
X minus R.
X minus R. Very good. Whatever x is, right? Take R away, and that's what that side is. Good. Now, what can you say about these two triangles? They are, they're both right triangles. They're proportional. They are similar triangles. Why are they similar triangles? This angle here is the same as this angle, isn't it? But that's the same as this angle. And they both have the 90 degree in the corner, which means that whatever this angle is, this angle must be, right? Similar triangles are triangles that have the exact same angles in them. And there's a property of similar triangles. So this is something that most Calculus 1 students need to go look at again, is properties of similar triangles. So here's what we can say. I'm going to erase all this. I'm going to do a quick little review of similar triangles. If you have two similar triangles, what you can say is that the ratio of the sides are congruent. The ratios of corresponding sides are the same. What the hell does that mean? It means this. If I take this side of the triangle here and take the ratio of that to this, if I write 20 divided by x, that must be congruent or equal to the ratio, the same ratio set up on the other triangle, 6 over x minus r. So the ratio of this side to this side must be equal to the ratio of this side to this side. That's one way you could have done it. You could also have done it this way. The ratio of this side to this side, 20 is to 6 as x is to x over r. So I can say that divided by that is equal to that divided by that. And then I could keep going. I could do, this over this is the same as this over this. Corresponding sides, set up ratios, they must be equal. Are you all with me on that? Sure? Any of these you could work with. I'm just going to work with the first one I did. Why am I going to work with this? What have I created? What have I created? An equation. What does it have in it? X and R. That's what I needed, right? But I had to come up with that using some knowledge of geometry. So once I have an equation, can't I differentiate it? I don't want to yet, though. I'm actually going to cross multiply this thing. And that way I can turn it into something that's a little easier to differentiate. So I just multiply both sides by x minus r, and then multiply both sides by x to get this. And then I can go even further. I can subtract 6x, get 14x, move the 20r to the other side. And I can go even further, dividing both sides by 2. I'm just doing algebra to try and clean it up as much as I can. I'll just stop here. Isn't that easier to differentiate than that? Now I'm ready to differentiate. So what is the derivative of that equation? Implicit differentiation with respect to t. So what's the derivative of 7x?
7.
7, just DXDT, right? So 7 is a constant. Derivative of x with respect to time is DXDT. Equals 10 DRDT. Now investigate that and tell me if you have everything you need. Do you have DXDT? That's what we're trying to find. Do we have DRDT? That's the speed of the guy. Isn't it? Did we need anything else? No. So I could say this, DXDT is equal to 10 over 7 DRDT. What's DRDT again? 7? So I can plug in and get what? DXDT is 10 sevenths times 7, which is 10. 10 what? Feet per second. I want everyone to look at this real quick right here. There's something kind of interesting about what that's telling us. The speed the shadow moves away from the pole is what? The speed of which the shadow moves away from the pole is 10 sevenths. Divide both sides by 7 here. 10 sevenths of the what? Speed of the guy. It has nothing to do with how far he is away from the pole. Look at that. Does that equation right there have anything to do, does it take into account at all, in that equation, do we ever have the actual r come into it? Do you see r in here anywhere? Did I ever have to plug in the fact that he was 12 feet away?
No.
No. In the formula for the speed of the shadow, it only required I know the speed of the man. That's all that mattered. That means that, believe it or not, the speed of his shadow moving away from the pole is constant. But it's moving away 10 sevenths of his speed, so a little bit faster than him. But it's the same the whole time, which may seem weird, but it's mathematically that's what's happening. Okay? So you may think the further he gets away, the faster it's going, but it turns out that it's moving the same speed the whole time. As long as he's moving the same speed the whole time. Interesting. All right. Man, we're not going to get through all of them. Conical cup. This will be our last one. We'll at least set it up. I want to at least get you to think about it. We have 15 minutes, right? So we're doing the conical cup one. A conical cup is 4 inches tall, 6 inches wide. Water is being poured into the cup at a constant rate of 2 pi cubic inches per second. How fast is the water level rising when the water is 1 inch from the top of the cup? So in this picture, again, if you watch the video, what I tried to express to you is that if you fill this up at a constant rate, that initially the water comes up very quickly, but as time goes on, it slows down. We're saying that the rate at which it's coming up slows down. So I think we've all seen this or experienced this like in the real world, right? You're filling something up that has some weird shape to it, and in the beginning it fills up fast, and then it might slow down towards the end. We want to know at a specific instant in time how fast it's rising. Okay? So I'm not going to draw the picture. I'm not going to put the picture out there for you. I'm going to just start this myself, all right? So here's the specific instant in time. At the specific instant in time, I have this conical cup, right? I know that I want to know what's happening when the water level is what? 1 inch from the top? I brought blue today. I know blue doesn't come out on the video very good, but it comes out in here, okay? So here's my blue water level, and let's just say that the distance from here to here is 1 inch, right? That's the specific instant in time that I'm talking about, right? Now, in general, we're just going to have some conical cup, and it's going to be, what? It's going to have some distance here to wherever the water level is. And it's going to change with time, isn't it? And what do I say here? Let's write down what we're given and what we want. Also, I didn't put this on my picture, but I had the dimensions of the cup, didn't I? It's 4 inches tall, so the whole cup is 4 inches tall. That would be in both problems, wouldn't it? 4 inches and 6 inches wide. That would be the same in both problems. The cup itself doesn't change its physical dimensions in the problem. The water inside, of course, does, doesn't it? What am I given? How fast the what? The volume is changing. So I can call that what? DVDT. And what is the rate at which it's changing? 2 pi. Cubic inches, right? Inches cubed per second. What is it that I want? How fast is the water level rising? Well, where's my water level? I don't have it drawn here, do I? I mean, here it is, right? I want to know how fast it's rising, so wouldn't that be relative to the bottom of the cone, like how fast this is coming up? So what should we call this then? L? I'm going to do this then. L, is that all right? For the level of the water? Is that okay with you? And I want to know how fast L is coming up. So we want D, L, D, T, and we want that when? At exactly the moment what? What's 1? When it's 1 inch from the top. When L is 3, good. When L is 3. Because 1 inch from the top means that if the cup's only 4 inches high, that means you've come up 3 inches. So it's exactly the moment that L is 3. Now that's perfect because what we want to try and do is have as few variables as possible. We don't want to start introducing, oh, I'll call this H, and then that's when H is 3, and you have 5 different variables. You want to do as much as you can with as little as you can. Okay. That's usually what we want in these problems. Something we're given, something we want, and at a moment in time. And a picture to go with it. So can you connect the volume to the frickin' length? Okay, volume of what, though? Be careful here. The volume of what? Of the water. Not the cup. The volume of the cup we know, right? I mean, it's fixed. 4 and 6. We already know what the volume of the cup is. But we want to know the volume of the water. So keep in mind that this represents volume of the water, not the cup. Can you find a formula that connects the volume of this water, that's the blue part here. Can you find a formula for the volume of this water here? Okay, that's the volume we're talking about. And the length, this length, which is actually the height of the cone, isn't it? So now you open up your little book and you start looking for volume formulas for cones. And you find one. And it says what? The volume of a cone is what? 1/3 pi r squared h, doesn't it? So if you look in a book, it'll have a cone drawn there. It'll have the radius here like this. It'll have the height like this. And it'll say the volume is 1/3 pi r squared h. Now for us in our problem, we don't have h. What do we have? RH is L. Why? Because that's what was suggested we use L. Thanks a lot. We should have used H. No, I'm just kidding. I'm just messing with you. But you see what I'm saying? If you call it something, then you got to know how that corresponds to your formula, right? I'm just giving you a hard time. So we know this is L. Now, that's actually pretty good because the volume of this water so far for us is 1/3 pi r squared L, right? That's for us. This is out of the book, but this is how it translates for us. We almost have an equation right now that relates V and L together, right? The only thing we don't have in here is R. Like, what's the radius of our water? No, that's the radius of the cone, not our water. So isn't our radius of our water changing? Like as the water level comes up, the radius of our water changes. So this is where you have to come in here and you have to do a very common technique with these problems, and that's you take your little samurai sword and you cut this thing right in half and you just look at it from the side. And instead of looking as a three-dimensional cone, look at it as two triangles. So look at it like this instead. Here's my cutting. I'm coming in here. There's my cup. And there's my water level. Okay? Do you all agree that's a cross section of the cone? And then what I'm going to do is I'm going to cut it down that middle like this. And notice what I have created again in this problem. Two triangles, haven't I? Forget the left side of this. I don't even need it. But I have now two triangles. I only put the little ripples there so you know I'm talking about the water, right? Yes? Okay, this is what? From here to here is what? No matter what? 3, because that is half of the cone. How high is the cone? 4. So I know that goes here to here, that's 4. Right? How high is this part, the water level here? How high is it? That's at the moment in time yet. We can't go there yet. L, right? That's L. Isn't it? And this right here is R. That's my little radius of my water. But don't I have similar triangles here? Don't I have a little triangle and a big triangle? Yes? So I have this. Here's my big triangle. It's 3 and it's 4. And then I have my small triangle like this. And it's what? L and R. So those are similar triangles. So what can I say? I can say a lot of things, right? How do you want to say it? 3 over 4 equals R over L. Or if you'd like, R is equal to what? Three-fourths L. Multiply both sides by L. Why am I doing that? Because if I have an equation now that has R in it, what can I do? Take that R and put it right there. See, what this is saying is that if you're in this cone, whatever the height of the water is, whatever L is, your radius is always going to be 3/4 of that. Your radius is always 3/4 of the L. So come into this equation now. 1/3 pi times the radius, which is 3/4 L, and then squared times L still. And now don't we have a formula for volume, connecting volume and L together? Right? Replacing R with this. This is equal to, let's see, you're going to have to square this, right? Square 3/4, what do you get? 9 over 36? Or 9 over 16, I don't know why I said that. 9 over 16, right? And then times 1/3. So I'm bringing that out here. So 9 over 16 times 1/3 is 3/16. I have 3/16 pi L what? L squared, but then L again, L cubed. And that's my formula.
Is that all it wants?
Oh no, now we have to differentiate that with respect to time, right? And then you have to plug in. So I'll accept that as a bonus first thing at the beginning of class next time. Finish that up for me. But we still have a few more problems to look at. You know, because these, I think I had 2 more. The runner and the ladder were the next 2 problems. I skipped one. Which one did I skip?
The angle.
Oh, the angle. Yeah, we got to get the plane flying with the angle too. So I'm guessing that what next class will look like is probably a good 45 minutes to an hour of related rates, followed by a kind of review of what to expect on the exam. But I can already tell you for the exam what you should be expecting. You should just be expecting derivatives, right? So I'll give you, they'll kind of like increase in difficulty. There will be the first few will involve some power rule, and then you'll get some product rule, and then you'll get some quotient rule, then you'll get some chain rule, then you'll get some implicit differentiation. And a lot of the rule problems, I'm just going to ask you for the raw derivatives. Just raw derivatives. And then there will be a problem or two in the test where you'll be asked to actually like find the equation of the tangent line to a curve. So you have to do a little more work. And then there's going to be the related rate problems. So these are going to be the beast problems in the test, I think.
So none of these problems are tested.
No, these problems will be on the test. Yeah, but I'm saying those will probably be the hardest because historically speaking, they are. And so what I'm thinking about doing is I might try and limit the number of related rate problems on the test by giving you a set of take-home related rate problems. Just like 3 problems or something that you can work on. But we'll see. Gotta think about it. Y'all have a good day. What's for next time? You don't need to watch any new videos. Try and do the homework for this section. 2-7.
If we come on Friday, can we do like a review, or is that weird?
Is that weird?
Like to finish up the review.
That is so weird. God, what a weirdo.
I don't know, like to review stuff, like all of
My office hours are for you to come in